This is the third video in our series on Lie algebras. And I'd like to point out that we're going through these first couple of videos fairly slowly to try to make this as accessible as possible. So perhaps if you're a student who's taken one semester of abstract algebra, these would be some nice videos. Versus most of the time when Lie algebras are presented, they're intended for maybe graduate students who have taken a couple of semesters of abstract algebra and passed maybe even a prelim in abstract algebra. So, we will get to some more advanced stuff later, but we're keeping it easy right now, or fairly easy. Okay, so let's recall a definition and then prove something, that goes along with this definition. So last time we looked at the notion of an ideal. And let's recall that a subalgebra I of a Lie algebra L is called an ideal if it has an absorption property. And this absorption property is similar to the one that you would have in rings. So for all x in L and I in I, bracket xi is inside of I. So you might say, well, inside of rings, this looks like it would be something called maybe a left, because you're left multiplying by an element of the algebra or ring and ending up in the ideal. But in fact, there are no left and right ideals in Lie algebras. And that's because you can switch the order of this bracket and just pick up a minus sign. So it doesn't really matter which entry is from the Lie algebra, the parent algebra, and which element is from the ideal. So let's just reiterate, all ideals inside of Lie algebras are two-sided. That's because we do have some sort of commutativity property within Lie algebras. It's just maybe anti-commutativity. Okay, so anyway, let's look at the following claim, which talks about how to build new ideals out of old ideals. And there's a similar claim in the world of rings for a couple of these. Okay, so let's suppose that I and J are both ideals of a Lie algebra L. Then so are, well, I intersect J, I plus J, which is everything of the form little I plus little j, where little I comes from I and little j comes from J. And also this thing that we'll call bracket IJ, which is the span of all of the elements of the form bracket IJ, where I comes from I and J comes from J. So this I intersect J, that occurs maybe naturally within regular rings or ideals of rings. And this I plus J also occurs in the world of rings. But this thing over here does not. Maybe there's like a I times J type ideal that occurs over there, but it's not exactly the same. Okay, so anyway, let's maybe leave this I intersect J as a homework exercise and see if we can prove that I plus J and bracket IJ are both ideals. Okay, so let's maybe suppose that we have I plus J inside of I plus J, and we have an arbitrary element x inside of L. And so what we want to show is that if we bracket x with I plus j, we end up inside of I plus j. So that means I plus j has this absorption property. I guess I should quickly say that, this is kind of automatically a vector subspace because we have sums of vector subspaces from linear algebra class. Okay, so anyway, let's go through the calculation. So maybe I'll just put here that we will note that if we take bracket I plus j, then by the bilinearity of the bracket, this will be xi bracket and then xj inside of the bracket. But then since each of these are individually ideals, we know that this term is inside of I, whereas this term bracket xj is inside of j. But then we're summing those. So that means this thing is most definitely inside of I plus j. But that's exactly what we needed to show that I plus j was an ideal. Okay, so we've taken care of the I plus j case. Now let's look at the bracket ij case. Notice here we're taking the span of those elements to keep everything closed. Okay, So let's maybe suppose we've got an arbitrary element, I'll call it y, inside of bracket ij. Well, what does that mean? Well, that means that y, well, it's a linear combination of elements which are of the form, you know, bracket little I, little j. So maybe we would write that as a1 and then bracket I1, j1 plus a2 and then bracket I2, j2 all the way up to an and then bracket in, jn. So that's the form of an arbitrary element in there. And now let's maybe just pay attention to what's happening for one of these pieces of y. In other words, one of the summands that we have right there. So let's maybe put a little observation right here. So if we were to do maybe x bracketed with, maybe I'll say ik, jk, because that would be like one of these elements, like I said, then we can rearrange this using the Jacobi identity to get something that we want. So what will it look like? Well, this will be negative jk with the bracket of x and ik, and then minus, let's see, bracket of ik with jk and x. So like I said, that's by applying the Jacobi identity. But now let's work inside out on these brackets over there on the right-hand side. So let's notice that xik being bracketed together is inside of I, because we know that I is an ideal. And then jk and x bracketed together is inside of j, because we know that j is an ideal and jk comes from j. But notice that we could apply skew symmetry here to move this over to the left-hand side, which sort of obviously makes this a term inside of bracket ij. And then notice here we've got an entry from I and an entry from j, so this is maybe naturally an element of bracket ij. Okay, great. But now if each of these individual pieces, when bracketed with x, is inside of bracket ij, then a linear combination of them will be as well. So from there it follows that y is inside of bracket ij, just applying like linearity to lots of terms like this. Okay, so now let's look at a special case of this third type of ideal. So now we know about the process of bracketing two ideals. It's maybe logical to say, well, what if you were to bracket the whole Lie algebra with itself? Well, in that case, you're going to get something called the commutator subalgebra. And there's some notation for that. So the notation is L prime. So like I said, L prime is bracket LL. So in other words, it's the span of all elements of the form bracket XY, where X and Y come from L. Okay, so now let's do a little exploratory example here to see if we can figure out the commutator subalgebra for a certain really nice Lie algebra. And the nice Lie algebra we're going to look at is GL2, maybe with entries in the complex numbers. Okay, so let's maybe take a natural basis for this, and the basis will be natural for finding the commutator subalgebra. So let's say this is like our basis. So maybe I'll take E to be equal to the matrix 0, 1, 0, 0. We'll take F to be the matrix 0, 0, 1, 0. We'll take H to be the matrix 1, 0, 0, minus 1. And then maybe we'll take something that I'll call little I to be, well, it looks like the identity matrix. I'm just going to use a lowercase letter just so that it's in line with everything else. So I think it's pretty clear that these are linearly independent and they span GL2C, which is pretty clearly four-dimensional. Okay, so now let's look at all possible brackets here. So let's do E with, or maybe H with E, but if you notice, this E, F, and H, were basis matrices for SL2C that we had seen before, and we calculated those brackets before. And what we found is that H with E was equal to 2E. But if 2E can be written as, well, a bracket, well, then that means that E can, just by dividing both sides by 2. But E being written as the bracket of 2 elements means that E is in the commutator subalgebra. So we would write E is in GL2C prime like that. Like I said, the commutator subalgebra. Now let's recall some other commutation relations or bracket relations. So H with F was minus 2F. Again, that's from some calculations we did maybe in the first video. But that tells us that F is also in the commutator subalgebra. Great, so F is in GL2 prime. Okay, good. And then let's also recall that if we bracket E with F, we get H. But that means that H is also in GL2C prime. Oh, but then the commutator subalgebra is really the span of elements like this. So that means the span of E, F, and H is a subalgebra of GL2C. So, well, what is the span of E, F, and H? Well, let's recall that those were the basis vectors for SL2C. So that means that SL2C, which, like I said, is the span of E, F, and H, is in fact a subalgebra of GL2C prime. And I know, well, it's kind of obviously a vector subspace. It's a subalgebra because, well, we know that it's a Lie algebra and it closes under the bracket. Well, notice that what we're missing is I. We haven't written I as the bracket of anything. But notice that we're not going to be able to write I as the bracket of anything, because these three bracket relations here represent all possible ways of bracketing E, F, and H that are non-trivial. And when I mean non-trivial, I mean they don't give you something zero. So let's maybe note that, for instance, if we were to do H with H, which is the same thing as E with E, or the same thing as F with F, which is really the same thing as doing I with anything, we would get 0. Well, that's because the identity matrix clearly commutes with everything, and then everything commutes with itself. Or maybe we also had this alternating thing, or property, I should say, that tells you that H, H, E, E, and F, F should all be 0. Okay, well, this kind of observation right here, together with these bracket relations, show us that I is in fact not an element of GL2C. It's impossible to get there. But I was the only thing missing apart from SL2 inside of the commutator subalgebra of GL2. So that means that, in fact, SL2C is equal to GL2C prime. In other words, the commutator subalgebra of GL2 is SL2. Maybe furthermore, let's note that just by these equations right here, we see that every element of SL2 can be written as the bracket of other elements in SL2. And that's because, well, every basis vector of SL2 can be written as brackets of basis vectors of SL2. So what that tells you is that SL2 prime really just equals SL2. So in other words, the commutator subalgebra of SL2 is simply SL2. Okay, so now that we've looked at this a little bit, and we're going to look at commutator subalgebras maybe in general in an upcoming video, now I'd like to look at homomorphisms, isomorphisms, and isomorphism theorems in the context of Lie algebra. Okay, so let's say we're given two Lie algebras, L1 and L2, and then a linear transformation phi from L1 to L2. So we say that linear transformation is a Lie algebra homomorphism if, well, it preserves the bracket operation. So in other words, for all xy in L1, phi evaluated at the bracket of x and y is the same thing as the bracket of phi of x and phi of y. So just compare this to a group homomorphism or a ring homomorphism and notice like it's exactly the same. It's just the operation is this Lie bracket instead of multiplication or whatever the group operation is. So if in addition phi is bijective, we call it a Lie algebra isomorphism. So that should be a familiar name. And then we've got these two, important subalgebras. So the kernel of phi, which is all the elements of L1 that get mapped to 0. So it's like the null space of a linear transformation. And then the image of phi, which is everything that gets mapped onto. So in other words, it's all y in L2 such that y equals phi of x for some x in L1. So now we're going to look at the following very classic result. There's a result like this for every sort of algebraic structure. This is called the first isomorphism theorem. So let's suppose that phi goes from L1 to L2 and it's a Lie algebra homomorphism. Then the kernel is an ideal of the domain. The image is a subalgebra of the codomain. And then finally, L1 mod, the kernel, is isomorphic to the image. Okay, so let's prove these, starting with the kernel is an ideal. So let's suppose we have x inside of the kernel of phi, and then we have y just inside of L1. And so our goal is for bracket xy to be inside of the kernel. Okay, so let's maybe note the following. So let's take phi of bracket xy, but since this is a Lie algebra homomorphism, this will be the bracket of phi of x with phi of y. But x is in the kernel, so phi of x is 0, so this is simply the bracket of 0 with phi of y, but the bracket of 0 with anything is 0. So, well, what does that mean? Well, if something gets sent to 0, then it's in the kernel. So that means that bracket xy is, in fact, inside of the kernel. I guess we really need to show that it is a vector subspace, but I think that's pretty clear, and that's something that you would learn in linear algebra. The kernel of any linear transformation is a vector subspace of the domain. Okay, great. So that's the first dot up there. So now let's look at the second dot, that the image is a subalgebra. So let's maybe suppose that y1 and y2 are inside of the image of phi. And what we want is bracket y1, y2 to be inside of the image of phi. But what does it mean to be inside of the image? So this means there exists what I'll call x1 and x2 inside of L1 such that phi of x1 equals y1 and phi of x2 equals y2. Again, that's exactly what it means to be inside of the image. But now let's look at the bracket of y1 with y2. And note that that's the bracket of phi of x1 with phi of x2, just by how we got y1 and y2. But then since this is a Lie algebra homomorphism, we can pull that out, and this is phi of the bracket of x1 and x2. But that's inside of the image because it's, well, something inside of phi. So this is pretty clearly inside of the image of phi. So that's what we needed to show this was in the image. Well, I guess it, again, needs to be a vector subspace, but the image of any linear transformation is a vector subspace of the codomain. So I think we're okay there. Now let's move on to the last dot. Okay, so next we'll show that L1 mod the kernel is isomorphic to the image. So we'll do that by defining an isomorphism. So I guess there's maybe a little bit more to this. You could say that there's a unique isomorphism or whatever, but we've left that little detail out. Okay, so we're gonna define something that I'll call psi, and it goes from L1 mod the kernel into the image, and it's defined by psi of L1 or maybe x plus the kernel of phi. Remember that it's gotta act on a coset. So elements of L1 mod kernel phi are cosets of that form, and it's going to be sent to phi of x. So now let's maybe show that this is well defined. That's probably the only really hard part of this. So let's maybe suppose that we have x1 plus the kernel of phi is the same thing as x2 plus the kernel of phi. That's how you start showing something's well defined. You suppose that some element has two different names, in this case x1 and x2, and you show that regardless of the name you've chosen, it gets mapped to the same place. Okay, but those two cosets being the same means that x1 minus x2 is inside of the kernel of phi. Oh, but let's note that that means that phi of x1 minus x2 is equal to 0. That's what it means to be in the kernel. But this is a linear transformation. I don't even really need to use the fact that it's a Lie algebra homomorphism at this point. It's a linear transformation. So that means I can split this up and I have phi of x1 minus phi of x2 is equal to 0, which means that, let's write it down here, phi of x1 equals phi of x2, but then let's pull this one off to the left and notice that that's psi of x1 plus kernel of phi, and off to the right, this is psi of x2 plus kernel of phi. So we've shown that regardless of the name you choose, the coset gets mapped to the same place. Okay, so it's well defined. Now let's maybe show that it's a Lie algebra homomorphism, although this is going to be essentially for free. That's because it's going to rely on the fact that phi is a Lie algebra homomorphism. So let's do psi of the bracket of x plus kernel phi with y plus kernel phi. But let's recall, in order to bracket those two inside of a quotient Lie algebra, you get, well, let's see, psi of bracket xy plus kernel of phi. That's the definition of the bracket inside of a quotient Lie algebra, as we saw last time. But now by the definition of psi, that'll be phi operated on bracket xy. But now in turn, that's the same thing as the bracket of phi of x with phi of y, because phi is a Lie algebra homomorphism. But now we can just pull that back to psi, and we'll see that this is the same thing as the bracket of psi of x plus kernel of phi with psi of y plus kernel of phi. Great. But starting over here and ending over there is exactly what we needed for this to be a Lie algebra homomorphism. Now let's maybe show that it's one-to-one. Okay, so now showing that this is injective. So let's suppose maybe that psi of x plus kernel of phi equals the psi of y plus kernel of phi. And where we want to end is that these are in fact the same coset. But using our definition of psi, this means that phi of x equals phi of y, but then subtracting over, we see that phi of x minus phi of y is equal to 0. But then using the fact that this is a linear transformation, we get phi of x minus y equals 0. But that means that x minus y is in the kernel. So here we have x minus y is inside of the kernel of phi, but then that means that the coset x plus kernel of phi is the same thing as the coset y plus kernel of phi. But look, starting here and ending here is exactly what we needed for this thing to be injective. And then what about it being surjective? Well, that's actually maybe the easiest part of this whole thing. So let's suppose maybe that y is inside of the image of phi, but that means that y equals phi of x for some x in L1. That's just the definition of the image. But now just let's attach x to a coset and then map with psi and we have it. So we'll do psi of x plus the kernel of phi. Well, that's going to be equal to phi of x, but that's going to be equal to y. So we landed on an arbitrary element of the image, meaning that it's surjective. So now we've covered all of the bases for this psi to be an isomorphism, which means, yes, these two are isomorphic. Okay, so let's move on. Now we're going to look at two, maybe what I'll call linked examples that are applications of the first isomorphism theorem. So let's first consider a map phi, which goes from GL2C into SL2C. And how are we going to define this map? Well, it's going to take an arbitrary 2 by 2 matrix, A, B, C, D, and it's going to send it to this like 2 by 2 matrix with trace 0. So here we'll have A minus D over 2, B, C, and then D minus A over 2. So pretty clearly by construction, that thing has trace 0. And also it's a linear transformation. That's easy to check as well. So now let's check that it's in fact a Lie algebra homomorphism. Because we're doing this like, fairly strange action here in this map, we really need to check that it's a Lie algebra homomorphism. So let's introduce a tiny bit of notation here, just so that kind of it eases everything up. Let's set capital A equal to the matrix A, B, C, D, and we'll set capital B equal to the matrix X, Y, Z, W. And now let's look at this. So if we look at bracket phi of A with phi of B, so that's going to be phi of A times phi of B minus phi of B times phi of A. But in turn, that's going to be equal to, let's see, a half A minus D, B, C, and then a half D minus A. So that's this phi of A. And then phi of B will be, let's see, 1/2 X minus W, and then Y, Z, and then a half W minus X. Okay, good. And then we'll just have it in the opposite order. So let's see, a half X minus W, Y, Z, a half W minus X. So that's for the first one. And then we have a half A minus D, B, C, a half D minus A. Okay, so there we have that. But now it's essentially just doing a bunch of matrix multiplication and really matrix arithmetic. And so I'll just show what it is in the end. So after doing all of that calculation, you end up with BZ minus CY in that entry. And then over here, you'll have B times W minus X, and then plus Y times A minus D. And then down here, we'll have C times X minus W, and then Z times D minus A. And then on the other portion of the diagonal, we'll have CY minus BZ. But now you want to unravel that in the other direction. And again, like after doing a bunch of matrix arithmetic, you'll see that that is phi on bracket AB. So this makes it indeed a Lie algebra homomorphism. But now let's look at the kernel. And the kernel is actually pretty easy to calculate here. So notice that A, B, C, D is inside of the kernel of phi if and only if phi of A, B, C, D is equal to the 0 matrix. I think that's pretty clear. But then that's if and only if our matrix 1/2 A minus D, B, C, 1/2 D minus A is equal to the 0 matrix. That's just applying our phi. But then that means that B and C are both 0 and A is equal to D. So that means that, in fact, our original matrix A, B, C, D was really of the form A, 0, 0, A. Okay, but then what does that really mean? A can be taken to be arbitrary, so that means that the kernel of phi is really all diagonal matrices that are not just diagonal, I should say, but they are multiples of the identity matrix. So we could summarize that here. So the kernel of phi is everything of the form A, 0, 0, A, where A is any complex number. Okay, so let's maybe summarize the final result of that at the top, and then we'll move on to a related example. So using this Lie algebra homomorphism, we determined that the kernel was just the space of all matrices which were multiples of the identity matrix, but that's really the same thing as the one-dimensional Lie algebra C, because it's a commutative Lie algebra and it's fairly clearly one-dimensional. Furthermore, this is a surjective map, so I won't check that explicitly, but you can pretty easily check that this is onto SL2C. Okay, well then what else do we need to do? Well, applying the first isomorphism theorem, we have GL2C mod the kernel, but I'll write the kernel as C, is isomorphic to the image, which is SL2C. Okay, so let's put a nice box around that. And then let's look at a related result. So let's take pi from GL2C down to just the complex numbers, where this takes a matrix A, B, C, D and sends it to its trace. So in other words, A plus D. So that's the trace. Now you can check this as a Lie algebra homomorphism. Maybe I won't do that. Maybe that's a little bit of a homework exercise to check that this is indeed a Lie algebra homomorphism. But then what's the kernel? Well, notice the kernel is going to be everything that gets mapped to 0, which is everything with trace 0. But we had a name for things with trace 0, and that was SL2. So that means the kernel of pi is simply SL2C. Furthermore, this is like onto for sure. So then we can apply the first isomorphism theorem. We'll see that GL2C mod SL2C is in fact just isomorphic to C. So these are kind of like dual results to each other. And then I'd also like to point out that last time we showed that SL2C was an ideal just from scratch. But this also really proves it's an ideal because it's the kernel of a homomorphism. Okay, so now I'd like to point out that this is really a special case of a certain result. And that certain result goes like this. Well, let's maybe write up the special case. So GL2C is really isomorphic to SL2C plus C. And really that's a direct sum. And that's because over here we have the span of, using notation from a previous example, EFH, and then direct sum. This is the span of, well, what we called I in a previous example. And furthermore, these three close a subalgebra, and then this one also closes a subalgebra. So that's really maybe what's happening underneath all of this, and that's why you get like these two dual results, because GL2 will decompose as a direct sum of SL2 and then, well, essentially diagonal matrices. Okay, so let's maybe look at the general version of this result. Okay, so here's like a general version of what we just saw. So if we have the direct sum of any two Lie algebras, I'll call them L1 and L2, then there are like obvious projections onto the components. So we've got pi 1 projecting to L1 and pi 2 projecting to L2. And let's recall that everything in L1 direct sum L2 can be thought of as an ordered pair x comma y, and pi 1 projects it onto x, and pi 2 projects it onto y. And then the bracket of L1 and L2 is like inherited from the two brackets of, L1 and L2 respectively. And then, well, it's pretty obvious that the kernel of pi 1 is everything of the form 0 direct sum L2, which that's just isomorphic to L2, meaning that L1 plus L2 mod L2 is isomorphic to L1. And then we've got a similar result here for pi 2. So there's really not a ton to check here. It's just like looking at all of the little details which fall out very, very quickly. Okay, so now let's look at the second and third isomorphism theorem. So let's suppose that I and J are ideals of a Lie algebra L, then I plus j mod j is isomorphic to I mod I intersect j. So this is the second isomorphism theorem. And now implicitly here, we're seeing that j is an ideal of I plus j, and I intersect j is an ideal of I. So maybe technically we would need to check those two statements, but we won't. We'll just check the isomorphism. So that's the second isomorphism theorem. And then the third says that if I is an ideal of j, then L mod I mod j mod I is isomorphic to L mod j. And I guess the fact that we're taking the quotient here implicitly says that I is an ideal of j. Okay, so let's maybe get to it. So for this first one, let's consider the following map. So I'll call that map phi, and it'll start at I plus j, and it will end at I mod I intersect j. And what will it do? Well, its input needs to be something of the form little I plus little j, and its output needs to be a coset. So a coset with a representative from I. So let's say that this is I plus I intersect j. So I think it's pretty clear that this is surjective. And then you can also check that this is a Lie algebra homomorphism, but I won't do that. Okay, so let's maybe analyze the kernel. So let's maybe notice that I plus j is inside of the kernel of phi if and only if phi of I plus j equals 0 plus I intersect j. So something's in the kernel if and only if it gets mapped to the 0 vector. But now that's if and only if I plus I intersect j is equal to 0 plus I intersect j. That's just applying the rule for phi. But then these two cosets are the same if and only if I is inside of I intersect j. Okay, but let's recall that all of these i's are inside of I. So that means that this holds if and only if I is also inside of j. So let's look at this. We have I plus j is in the kernel of phi if and only if I is inside of j. But notice that this j is already inside of this j, so that means that this is if and only if little I plus little j is inside of j. But that means we have determined the kernel. So we see that the kernel of phi is in fact j. But now we can apply the first isomorphism theorem, and applying the first isomorphism theorem, we have the domain mod the kernel. So in other words, I plus j mod j is isomorphic to the image. But we said that this was surjective. It's fairly easy to check, so that establishes this second isomorphism theorem. Now let's move on to the third. Okay, so moving on to the third isomorphism theorem, let's start by defining a homomorphism. So let's take psi, and it's going to go from L mod I to L mod j. And we want the kernel to be j mod I so that we can apply the first isomorphism theorem. And how are we going to define this? Well, psi needs to be defined on a coset, so it takes x plus I to x plus j. Okay, great. And now let's first show that this is well defined, which is something you always have to do whenever you're working inside of a quotient space, because elements can have maybe different names. Okay, so let's suppose that x plus I is the same thing as y plus I. But notice that that means that x minus y is inside of I. But let's look up here. Notice that we assumed that I was a subset of j. So that means that x minus y is also inside of j. But in turn, that means that x plus j, the coset, is the same thing as y plus j, the coset. Because again, x minus y is inside of j. But then working off to the left, this is exactly psi of x plus I, and this is exactly psi of y plus I. So there we've done it. We've shown that regardless of the name for the input, we get the correct output. So now let's show that we indeed have a homomorphism. So let's see, we need to do psi evaluated on the bracket of x plus I with y plus I and show that everything like works out, if you will. So applying the bracket for the quotient, we see that this is psi of bracket xy plus I. It's that coset. But then applying the rule for psi, we see that that is bracket xy plus j. But now we can just bring that back out. So that's the same thing as the bracket of x plus j with y plus j. Again, because of how we define brackets inside of quotients. But now that's exactly the same thing as the bracket of psi with x plus I and psi with y plus I. But then that's exactly what we needed to be a Lie algebra homomorphism. Okay, so now let's see about the kernel. So maybe we can fit that in right here. So let's see. Let's note that x plus I is in the kernel of psi if and only if we have x plus j is equal to 0 plus j. That x plus j is just psi evaluated to x plus I. So in other words, psi maps that thing to the 0 vector inside of the quotient. But these two are the same if and only if x is inside of j. But now, if x is inside of j, then x plus I is inside of j mod I. So this is only if and only if x plus I is inside of j mod I, because the representative there is inside of j. But then let's look at this. We have this is inside of the kernel if and only if it's inside of that quotient j with I. But then we can apply the first isomorphism. So the domain mod the kernel, which in this case is j mod I, is isomorphic to the image. I guess we didn't check that it was onto again, but these are maybe constructed to be onto. So that proves this last result. Okay, so now I'll leave you with some exercises. Okay, so here are 3 nice exercises. The first is to find a subalgebra of the Witt algebra that is isomorphic to SL2C. Next up, let's find the commutator subalgebra of the Witt algebra. And then finally, let's consider the following Lie algebra of matrices. So notice they're 3 by 3 matrices, but you really only have 3 degrees of freedom. So they're of the form 0 minus A3, A2, A3, 0 minus A1, and minus A2, A1, 0. And this is over real numbers. And then what we want to do is show that there is a Lie algebra isomorphism from R3 to L, where in R3 the operation is the cross product. So in other words, bracket VW is really V cross W, whereas over there in L the operation is the standard commutator. And I guess I didn't write the map here, but the map takes A1, A2 to A and A3 into, well, a matrix of this form. So 0 minus A3, A2, A3, 0 minus A1, minus A2, A1, and 0. So that's your map. So that really shows us that even though this Lie algebra of the cross product seemed like a little bit different than other finite dimensional Lie algebras that we had seen, which were generally matrix Lie algebras. Well, in fact, it really is a matrix Lie algebra. Okay, and that's a good place to stop.